In this talk, I'll describe our work counting perfect matchings and the 8-vertex model. This is joint work with Jin-Yi. In the first part of this talk, I'll introduce the 8-vertex model and some previous results. The 8-vertex model is defined on 4 regular graphs. It was originally proposed in statistical physics on the square lattice. The states of this model are orientations of the edges such that the n degree of every vertex is even, the L degree of every vertex is also even. The states are called even orientations. There are 8 permitted type of local configurations around vertex, so there are 8 possible energy parameters epsilon 1 to epsilon 8. So the original form of the partition function of this model is given as follows, where the beta larger than 0 is the inverse temperature. I will give a simple form on the next slide. So in this work, we assume arrow reversal symmetry. This is also called the zero field assumption in physics, where we assume that if we flip all the arrows around the vertex, the weight is not changed. So epsilon 1 equal to epsilon 2 and so on and so forth. So if you look at the partition function defined on the last slide, it's really a function of these exponential things. So we simplify our notation and use A, B, C, D as our parameters. And the partition function is the sum of the weights on the underlying even orientations, and the weight of each even orientation is a product of the weight on every vertex. So in this paper, we assume A, B, C, D are all non-negative. We note that the weight D are the weights on sink and source. And for all other 6 configurations, there are 2 arrows going in and 2 arrows going out. The special case when D is equal to 0 is called the 6-vertex model, whose states are Eulerian orientations, so 2 in, 2 out, rather than even in, even out. The 6-vertex model was introduced by Linus Pauling in 1935 to describe the properties of water ice and is one of the most studied models in statistical physics. The 8-vertex model was introduced by Sutherland and Fan Wu, with the advantage that it's being very expressive on square lattice. For example, it can not only encode the 6-vertex model, but also can express the dimer model and the zero-field Ising model. Baxter achieved a good understanding in the thermodynamic limit on the square lattice. In physics, it's called an exactly solved model. In terms of exact computational complexity, the 8-vertex model is very well understood. On general 4 regular graphs, in 2017 we have a paper on this, and in that paper the author studied the 8-vertex model in the full 8 parameters in the complex domain. Here we're assuming arrow reversal symmetry is only 4 parameters, and we also assume they are all non-negative real numbers. So in our setting, the problem's Sharpe is proved to be Sharpe hard unless either A equal to B equal to C equal to D, or at least the 3 of A, B, C, D are 0, or 2 of A, B, C, D are 0, and the other 2 are equal. We also note that on planar 4 regular graphs, the FKT algorithm can be used to compute the partition function when A squared plus B squared is equal to C squared plus D squared. So the next part, I will describe the approximate complexity and our results. If a statistical mechanics setting, the square lattice 8-vertex model exhibit different macroscopic behaviors under different parameter settings ABCD due to the change in the inverse temperature beta. Recall that ABCD are coming from the exponential function of the minus beta epsilons. In the disordered phase, which we use to denote the high temperature regime, we have that each of ABCD is less than or equal to the sum of the other 3. So no one of ABCD is dominant. And in the ordered phase, or in the low temperature regimes, we have that one of ABCD is dominant. So we will use the following notations in describing our results. We use this X to denote the inside part of this pink red region. It is also the disordered phase. We use Y to denote this left oval. We use Z to denote this right oval. They are both inside this rectangle X, but they do not contain each other. So here are some terms. Please feel free to pause and read the definition of an FPROS. We use Sharpe PM to denote the problem for counting perfect matchings on general graphs. The approximate complexity of Sharpe PM is a central open problem in this field. But on the bipartite graphs, it is already solved. The number of perfect matchings is, in this case, is equal to the permanent of an n by n 0, 1 matrix. Jerome Sinclair and Jerome Sinclair and Vigoda give an FPROS for estimating the permanent of an arbitrary n by n matrix with non-negative entries via Markov chain Monte Carlo, or MCMC. So now we're ready to describe results in the approximate complexity. So the only previous results is by Greenberg and Randall. They proved the torpid mixing of a specific Markov chain when the weight D is very large. This is when the temperature is low. So this Markov chain flips the orientations of 4 edges along a uniformly picked face at each step, according to the Gibson measure. This means that when the sinks and sources have large weights, this particular chain cannot be used to approximately count or sample 8-vertex configurations on the square lattice according to the Gibson measure. Recently, my collaborators and I worked on the approximate complexity of the 8-vertex model on general 4 regular graphs. Our results are reported in 2 papers. The first is a CCC paper where we show that approximating the partition function is NP-hard outside X, namely in the ordered phases. Another result in that paper is that there's an FPROS in this green region, is Y intersecting Z. Our method of approximation is also via MCMC. And in this work, we relate the approximate complexity of the partition function of the 8-vertex model to counting perfect matchings. So first result is that outside this Y, which is the red together with the blue, the complexity is at least as hard as counting perfect matchings on general graphs. And the other result is that inside Z, which is green together with blue, approximating the partition function can be reduced to counting perfect matchings. So combining these 2 results, we know that in this blue region, in this Z minus Y, the problem is equivalent to counting perfect matchings in approximation complexity. Another result is that we report in CCC paper is that there is an FPROS for the partition function in a subregion of Z minus Y on planar graphs. So combining these results, we know that the yellow region is Sharpe completing the exact computation, Sharpe PM equivalent in approximate computation on general 4 regular graphs, but admits an FPROS in approximate computation on planar 4 regular graphs. So to our best knowledge, they are the first identified problems having these 3 properties. So now let me describe our proof strategy for the Sharpe PM hardness result. Recall that we want to show that outside of Y, in this red and blue region, the computation is at least as hard as counting perfect matchings. So first let me introduce the easy model partition function. It has a parameter gamma, and the partition function on a graph G is defined to be the sum over all the 0, 1 configuration on its vertices, and the weight is on the edge. So Goldberg and Jerome proved that when gamma is less than -1, then counting perfectly matching is equivalent to the Ising partition function. This reduction is a approximation Prism reduction. Okay, so our proof strategy is as follows. First, we show that we identify a region y complement bar, y bar prime inside the y bar, such that the computation of the partition function, the Sharpe 8v, is equivalent to the Ising problem with some gamma less than -1. So this proves that in this region y bar prime, the computation is equivalent to counting perfectly matching. This was achieved by using a holographic transformation and a non-local mapping. In the second part, we proved that the computation inside y bar is at least as hard as the computation in y bar prime, but with the additional assistance of parameters 1 epsilon, 1 epsilon, 1 epsilon, 1 epsilon. So this means that given a graph, there are some vertices that's with parameter ABCD, and we can also use some other vertices with parameters 1 epsilon. And each 1 epsilon is a number that's sufficiently close to 1. Its distance from 1 is smaller, no larger than an exponential function, inverse exponential function in n to the c, where n is the number of vertices in the graph. And we achieve this using a constant size Fourier reconstruction. I'll describe what's a Fourier reconstruction. So the last part, we want to show that using only vertices with ABCD, we can obtain a virtual vertex with parameters 1 epsilons. This is achieved by using a polynomial size for reconstructions. So I will not describe the specific proof for the first 2 points. I will only describe the proof for the last point. What is a Fourier reconstruction? It is a four regular graph having 4 external edges. This defines a constraint function. For a particular input orientation, the value is the weighted sum of all valid internal configurations consistent with the input. So if everything inside, every vertex inside satisfies the even degree rule, then this gadget as a virtual vertex also satisfies the even degree rule and the error reversal symmetry as well. And we can denote the weights of this virtual vertex by A prime, B prime, C prime, D prime. So, so we have multiple iterations of constructions for the last parts of our proof. A single step in this iteration is as follows. So we assume in the last iteration we get the following result: 0 less than the weight on secant source, D sub I, and it's the smallest weight of among the ABCD. And Ci is the biggest. So we use one of the 2 constructions on the right-hand side to obtain a virtual vertex with ABCD in the next round, satisfying the following conditions. The first is that D sub I plus 1 is still the smallest weight among the 4. And element-wise, the ABC over D get shrunk. So they do not increase. And the last part, and it's the most important part, that the distance between previously the largest gap, Ci minus Di, after normalization gets shrunk, and it gets shrunk quadratically. So we use one of the 2. It depends on the weight of Ai, Bi, Ci, Di. And the last step is to prepare for the next round. We permute A sub I plus 1, B sub I plus 1, C sub I plus 1 to get A tilde, B tilde, and C tilde, so that we still have this condition. This can be achieved by relabeling the edges. And yeah, so the construction of the polynomial size for reconstruction is as follows. First, we assume that this condition is satisfied. If it's not the case, we can achieve this virtual vertex with such weights using constantly many vertices, starting from any ABCD. And we repeat the single step on the last slide, logging many times. So each time we're using 4 times growth of, we're using 4 times more vertices compared with the last step. So after logging many steps, we have a polynomially large for reconstruction. And finally, we normalize by the d sub c log n. Because each time the weight is shrunk quadratically, after log n many times is shrunk exponentially in the base. So the last part is the proof for the Sharpe PM easiness result. Recall that we want to prove that in this green together with the blue region, the approximation of the partition function can be reduced to contain Sharpe PM. So first, let me introduce what's a match gate. A K-ring match gate is a graph with k external edges labeled from I sub 1 to I sub k. Each non-external edge has a non-negative weight. Similar to a Fourier construction, it also defines a constraint function on the k external edges, where the value for a particular input is the sum over all the configurations inside consistent with this input. But this time, we're not summing over even orientations, but we are summing over perfect matchings. Planar match gates with complex edge weights has been completely characterized, like partition function of systems with vertices can be represented by the planar match gates can be solved using FKT algorithm. There is an FPRS for counting perfect matchings on bipartite graphs, as I described earlier. Here we study match gates with non-negative edge weights, and the match gates we study are not necessarily planar or bipartite. It was proved that allowing non-negative edge weights does not add more power to the unweighted Sharpe PM problem in approximate complexity. So our strategy is that we want to reduce the partition function of the 8-vertex model in the region Z on a four-regular graph to the sum of weights of perfect matchings on another graph. So basically this is a reduction where each even orientation corresponds to a set of perfect matchings with the total weights being preserved. So for this reduction, we really need 2 kind of gadgets. The first is a two-array match gate representing an arrow. So we'll use a vertex with 2 dangling edges. This is a vertex with an edge on the left and an edge on the right. So we set the following convention. If it's an arrow is going in, we set a correspondence of this two-array match gate such that the left edge is matched, but the right side is not matched. And correspondingly, if we want to denote the arrow is going to left, then we match the right side of this match gate, but with the left side unmatched. So the next step is to represent a degree 4 vertex with ABCD in the region Z by a Fourier match gate. So we'll use a 6-click with 4 external edges. If we give a weight W sub ij to the edge connecting vertex I and vertex j, we can compute the function that's represented by this Fourier match gate. So how do we get this? So F0011 means that we're summing over all the perfect matchings inside this Fourier match gates such that the edges connecting to 1 and 2 are always not matched. The edges connecting to 3 and 4 are always matched. So in this case, 1, 2, 5, 6 are not matched. And we have really 3 options to make a perfect matching under such situation. The first one is match 1, 2, and 5, 6. This is represented by this W1 to W5, 6. The second way is to match 1, 5, 2, 6, represented by the second term. And the third way is to match 1, 6, and 2, 5, represented by the third term. So if we replace, given a four-regular graph in the 8-vertex model, if we replace each vertex, degree 4 vertex, with such a Fourier match gate, then it's the partition function, then the sum of weighted perfect matchings is effectively the partition function of the 8-vertex model with the following parameters: A1, A2, B1, B2, C1, C2, D1, D2. So we do not necessarily have ever reversal symmetry. And the question is that can we set these 15 edge weights W sub ij's so that we can get any f satisfying the following condition. If we can do that by restricting error reversal condition, we get the region C. So we have to do some analysis, and the problem finally reduced to the following geometric lemma. We have 3 regions: capital U, capital V, capital W. We want to show that use the Minkowski sum of V and W. So how do you do that? We use a geometric proof. In this picture on the left, the region V is denoted by the face bounded by this red triangle, and the region W has 3 facets, and they are intersecting as the 3 blue rays. And the region U has 7 facets, and the 7 facets intersects at the red triangle together with this green rays. In order to show that U is the Minkowski sum of V and W, we simply take this blue part, which represents V, and take this vertex of the 3 blue rays and swipe it through the face of this right triangle. In this way, we can show that the space of U is fully covered. Some remarks. So our result is tight. It can be proved that no ABCD outside Z can be implemented by a match gate. And it is open for several years what are the constraint functions that can be implemented by non-negatively weighted K rematch gates for K larger than 3. Here we give the characterization for 4 rematch gates. They are essentially those satisfying this condition. So this solves the problem for K equal to 4. And thanks for watching.